Now with a background understanding of what the von Mises equivalent is, we need to walk through what ERA is doing when it provides us with a limit curve. And what I've got here is a real simple example of a 16,000 foot vertical well. There's 5-inch drill pipe and a lightweight BHA in the string. Actually there's no BHA in the string. We're trying to keep it very simple. Just 5-inch 1950 S135 drill pipe to surface. No tortuosity in the well, just perfectly vertical. And if I was to look at the driller's view plots of tension and torque for this well, you would notice when I'm not rotating, there's no torsional load. Even if I was rotating, there would not be a torsional load since it is perfectly vertical. But you notice on the driller's view plot, we've got the tensile load in green and then the limit curve in black. And that's actually the maximum allowable tension that the driller could see without exceeding the design factor limit of the pipe. Now we've assumed that we've got premium class drill pipe, and premium class drill pipe has a 12.5% reduction in nominal wall thickness in order to determine its tensile capacity, and then of course we overlay a design factor on top of that rating. Now what's completely different in ERA compared to TAD and any other commercial software is that the limit curves are calculated based on the total VME envelope. And what that means is if I have a combination of pressure on the inside or outside of the pipe, torque on the pipe, tension on the pipe, or compression in the pipe, or bending in the pipe, then the maximum allowable tension or torque or whatever load we're concerned with will take those other loads into account. And that's why sometimes we see some counterintuitive or confusing shapes to the limit curve. The tension plot is an example where everything kind of is as you would expect, where we've got just a linear relationship with depth. Since it's all 5-inch drill pipe, it's just a straight line limit of about 460,000 pounds of tension. However, the torque plot on the right, what that's meant to convey is how much torque can be applied at surface before we overload some component in the string as the bit gets deeper and deeper. Remember, again, this is a driller's view plot. As the bit gets deeper in the well, what's the maximum torque the driller can see before we overload the string. And you notice that we've got this sloping curve shape. That's due to the fact that the tension in the string is, of course, getting higher and higher and higher as the bit gets deeper and deeper and deeper in the well. If we were to swap over to the snapshot view, that would help explain a little bit about what's going on. So at snapshot view, 16,000 foot bit depth, you can see the tension in the string on the left, torque in the string, in the middle, and then the VME equivalent on the right. Now, since there's no torque load in the string, we don't actually see the torque load curves with the current assumptions that I have. But you notice that I do have my torque limit lines in pink. The dark pink is the pure torsional limit of the pipe at premium class conditions, and then the slightly lighter shaded pink is with the design factor 1.2 applied. And what would help kind of explain what's going on here is if we were to drag the string up the hole and we were at a shallower depth, you could see that with less tension in the string, I can apply more torque safely without overloading the tube. When I'm very shallow in the well and there's hardly any tension, well, I can apply, all the way up to almost 50,000 foot-pounds. But as the string gets deeper and the tension in the string increases, of course, I can't apply as much torque. I'm using up more and more of the capacity of the pipe. If I was to apply overpull, let's say I'm in a stuck pipe situation and I had to apply overpull to the pipe. Let's say that I apply negative 160,000 pounds of pull, negative 150,000 pounds of pull. I would be right at, let's say 140. I would be right at the design factor tension limit, and you would notice that there would be almost no available torque capacity in the pipe. And then, of course, over here on the right, the VME load is right at the design factor limit. If I was to apply just a little bit more overpull, then you'd see that I have zero torque capacity essentially, and I'm just at the threshold. So 145,000 pounds overpull is the absolute limit. What that doesn't tell me, though, is the combined load limitation. I take away the overpull, and I say, all right, I'm in a stuck pipe situation, and I'm going to hold some torque in the string. Let's say that I hold 15,000 foot-pounds of torque in the string. You can see that my torque load just appeared, and if you didn't catch it, the tension limit has just been reduced. It was at 465,000, and it's just dropped down to about 440,000 pounds. If I remove the torque, you'll be able to see the lines change. And if I return the torque, you'll see them move again. So now if I go through the same exercise and I say, okay, what's the maximum allowable overpull that I can apply? And I say, all right, I want minus 100,000 pounds. What would that look like? Maybe minus 120. Yeah, right there at the limit at 120,000 pounds of overpull with 15,000 foot-pounds of torque applied. In all three plots, you notice I'm at the limit with all three plots because all three are coming back to this VME design factor as the basis for the maximum applied combined load. Now, if I was to be pumping on the string, say that I'm pumping at 900 GPM, of course, there's now going to be internal pressure. And if I'm pumping simultaneously, now I've just exceeded the capacity of the pipe. So with flow rate and pressure on the inside of the pipe, I can't pull as hard. I'd have to reduce my overpull to, let's say, 100,000 pounds. So this is very useful when you're working in a stuck pipe situation. It's also very useful when we start having complex strings, such as tapered strings. So let's change the problem a little bit. Take off the flow rate. I'm going to modify my string now to reveal that this is actually tapered. I'm going to extend it. Let's say that I've got a couple thousand feet of 5.5 drill pipe on top. Now, of course, the 5.5 drill pipe has a lot higher tensile capacity than the 5-inch drill pipe. And as I start to apply my load, say where were we at, 120,000 pounds of overpull, 130,000 pounds of overpull, 140, 150, 160. At 160,000 pounds of overpull capacity, I've exceeded the limit of the 5-inch drill pipe itself, not the 5.5. I'm still within the capacity of the 5.5, but the 5-inch has been exceeded. If I was to go to the driller's view plot, you would notice that the shape of the curve now has changed. My tension limit capacity is a straight line until I start picking up the 5.5 drill pipe, and then it has a sloped shape to it as I get deeper. And that slope shape mirrors the tension that's actually in the string. So I really can't go beyond about 14,000 feet before I'd exceed the tensile capacity of the pipe if I was to apply 160,000 pounds overpull with 15,000 foot-pounds of torque held in the string. Now this gets a lot more complicated when we have a directional well and we add any kind of bending load, or we've got different torque and drag factors going on behind the scenes. So right now I'm just trying to keep it real simple, show you where those limit curves are coming from. In the next video, we're going to walk through some of the intricacies of which limit curves to choose to display and which ones you should not display. But this is just a quick introduction to where the limit curves come from and why they have a weird shape sometimes. If you always go back to the snapshot plot, it will help make sense of what you're seeing. Remember, this is unique to ERA. It's not available in TAD, nor is it available in any other commercial software. It's a very powerful way to make sure that we're not exceeding the capacity of the pipe.